Cleaning oil spills and storing carbon dioxide. New insights into porous media. Porous media are all around us. From natural materials like soil, sand and rocks, to everyday products like sponges, filters, diapers and concrete. These materials contain tiny spaces, or pores, that hold liquids or gases. When you soak up water with a sponge, for example, the pores fill with liquid, pushing out the air. The same process happens underground, where porous rocks store water, oil, or even carbon dioxide. Understanding how fluids move through porous materials is essential for solving real-world problems, such as cleaning up oil spills, improving water filtration, developing better batteries for electric cars, and storing gases underground to fight climate change. Despite years of research, fluid movement in porous media remains a complex puzzle. Now, scientists at the University of Stuttgart and the University of Manchester are making exciting breakthroughs by combining cutting-edge experiments with advanced mathematical modelling. One of the biggest challenges in this field is understanding how one fluid displaces another, like when water replaces air inside a sponge. Predicting this process mathematically has been difficult, and no existing model was able to fully capture it. To tackle this, the researchers used high-tech microscopy and advanced image processing to observe how two immiscible fluids, liquids that don't mix, move through porous materials. Their findings revealed that the definition of fluid flow paths, called preferential flow paths, should be revised. The shape and distribution of these paths does not only depend on the solid structure, but also on factors such as fluid velocity and viscosity. These insights are crucial because the efficiency of many real-world applications, from filtering water to injecting carbon dioxide underground, depends on the formation of these flow pathways. In another study, the researchers examined how dissolved substances, called solutes, spread through porous media that are only partially filled with the liquid. Using an advanced imaging technique called synchrotron-based X-ray computed microtomography, they captured high-resolution images showing how solutes travel through fluids. The results were unexpected. Instead of spreading evenly, the solutes moved unpredictably, arriving earlier than expected in some areas, while lingering much longer in others. Even more surprising, the researchers found that solutes spread faster when only half of the pores were filled with water compared to when they were fully saturated. These findings challenge existing models and could lead to more accurate predictions for processes like groundwater contamination and chemical transport. Building on these findings, the research team developed innovative visualization techniques to analyze how different factors, such as viscosity and pore structure, affect fluid movement. They found that even small changes at the microscopic level can dramatically impact how fluids flow on a larger scale. For example, in a solid structure made of circles versus one made of octagons, the number and depth of branching fluid pathways differed significantly. By combining advanced experiments, imaging technologies, computer simulations, and new visualization methods, these researchers are paving the way for a new generation of fluid flow models. Their work has exciting implications not only for industrial applications, but also for critical environmental efforts, such as improving oil spill cleanup and optimizing carbon storage to combat climate change.